Okay, our last lesson in this unit, we're talking about resonance and how it relates to music in tubes. Lots and lots of good demonstrations, and probably even demonstrations that you've seen before. A lot of you have probably seen these things called boom whackers, or they're basically just different length tubes. And when you crack them together, they will produce different sounds. Many of you have seen water glass resonance, where water glasses that are filled with different heights of water will produce different sounds. And of course, you can do all of these demonstrations on your own if you have the time. Now, I have a class set of these, so we're going to look at these in class together and try and make some music, because each of these is cut to a very specific length. And of course, they will produce different frequencies because they have a different length, as we're going to learn today. Um, Speaking of tubes with different lengths, sometimes in university, folks make musical instruments. This is PVC tubing, and this is a guy that made this at university. Students and residents sometimes have a lot of time, but you can hear. Anyways, it's a very illuminating presentation. I highly recommend you YouTube search that and watch it. Maybe we'll watch it in class together. Anyways, as you may know, wind instruments, which are traditional brass instruments and of course woodwind instruments, the source of vibration is of course different. One, of course, the brass instruments uses lips and the woodwind instruments uses a reed. But the premise is that these instruments are nothing more than really fancy pipes. Okay, so tubes, they're really, really exquisite tubes, and air is going to flow through these, sound is going to flow through these, and depending on, of course, the length of these tubes, and we can shorten them and lengthen them with these little valves up here, we can get very different sounds out of them. And so, that really takes away from the magnificence of how these things are created. There's a lot of really good and interesting and complex physics that goes into these things, but we're going to take a step back, and for the purposes of grade 11, we're going to say, okay, these are just really fancy tubes. So one thing that we talked about when we talked about reflection of sound waves, right, was that we've got two different types of tubes. We've got a tube that's open here and open here. But then we've also got a different type of tube that might be open at one end and closed at one end. And we get different sounds from these things because of different phenomena. So a tube that's open at both ends, what kind of a reflection do we see at the open end when a pulse or when a wave reflects off of a less dense barrier? Do we see a phase shift or do we not? And you should be saying, because you've read in your textbook, you do not see any kind of a phase difference. So the pulse would come down on this side, and of course it's reflecting off of a less dense barrier, and it would bounce back on the same side. When we have a closed end, or any tube that's got a closed end, we would have a pulse that would travel down, and of course this would be a more dense barrier, and that tube would then bounce back inverted. And so based on these two different things, we're going to create standing waves in different ways. So we have to always consider whether tubes are examples that are open at both ends, or whether a tube is perhaps open at one end and closed at one end. Okay, so these are some of the things that we're going to consider. The following diagram, and I'm going to put it up in a moment, represents basically how standing waves look in closed and open pipes, right? But there's a general rule for the location of nodes. Standing wave patterns in tubes have a node at any closed end and an antinode at any open end. Everything that I'm about to put up, we could construct together from scratch. But as you can see, there's a lot of information here. And so I've given you this chart so that we can investigate together. Here is a tube that's closed at one end. And this is what we're going to investigate first. Then we're going to turn our attention to this guy over here, which is a tube that's open at both ends. So let's begin. The rule states that every single tube must have a node at any closed end and an antinode at any open end. And so if I wanted to find the fundamental frequency, which is the lowest frequency or the largest wavelength that I could fit into a tube that's closed at one end and open at one end, this would be it. It would be a quarter of a wave. And this would produce a really long wavelength. But this would be about as large a wavelength as I could get and as low a frequency. From here, though, because of my rule, and because of the rule that states I have to have a node at this end and an antinode at this end, I can't go to a half a wave, because half a wave would mean that I'd have to have a node at this end, and I can't have that. So I have to skip to, instead of 1/4 a wave, I can't go to 2/4 of a wave. I have to jump to 3/4 of a wave, and we call this the third harmonic. In a similar fashion, I can't have 4/4 of a wave. I need to skip to 5/4 of a wave, and that's called the fifth harmonic. So these are all the different resonant lengths that we can create in a tube that's open at one end and closed at the other. This is a labeling system. The harmonics skip every single one. This is the first resonant length, the second resonant length, the third resonant length, and so on, but the harmonics and what we call them skip. Here's a tube that's open at both ends. The shortest wave, or excuse me, the longest wave and the lowest frequency that can fit in here, because of our rule, we need to have an antinode at this end and an antinode at this end, is that a half a wave is the shortest that fits. The next shortest is one full wave, antinode, antinode. Then we go to 3/2 waves. Then we go to 2 waves. Then we go to 5/2 waves. This is known as the first harmonic in this type of tube, the second harmonic in this type of tube, the third harmonic in this type of tube, and so on and so forth. The trick becomes to be able to use these things in problems. And so very often we need to unpack the problems that we're given. Here, the length of the tube is equal to 1/4 of a wave. Here, the length of a tube is equal to 3/4 of a wave. Here, the length of a tube is equal to 5/4 of a wave. And just like how we created our formulas for the internodal distance, we can now say, oh, we're going to relate, instead of talking about internodal distances, because that was for strings, we're going to talk about the length of the tube and how it relates to lambda. Over here, we've got half of a wave, we've got a full wave, 3/2, 4/2, and 5/2. So for all of these, our general formula, internodal distance, still applies, right? So this is for any standing wave at all. But we have a couple extras now. We have a couple extras where if we restrict this and we use this for strings and standing waves in general, and now we add a couple of these extra formulas over here, we can say that, hey, the tubes that had one closed end, first of all, were all divided by 4. They were all in quarters. And this little relationship, 2n minus 1, was one that gave me, if n equals 1, I get 1. If n equals 2, I get 3. If n equals 3, I get 5. This little expression right here will give me the different harmonics for all the different resonant lengths. Over here, I get L equals n lambda over 2. And this is basically used for tubes basically that are open at both ends. So I've added some formulas, and now we need to see how we use them. So let's take a look at an example. An air column that's open at both ends is 1.5 meters long. You'll see right away that this question specifies it's an air column, it's a tube, it's open at both ends. So I know which formulas I need to concern myself with. So this is all about unpacking the problem, understanding that this concept of a tube that's open at both ends relates to specific mathematics, and then I'm being given a length. A specific frequency is heard resonating from the column. What is the longest wavelength and its associated frequency? Longest wavelength means highest frequency, so the fundamental frequency, that could be responsible for this resonance. Speed of sound today happens to be 345. So let's take a look at what we know. We know the length of the tube. We know the speed of sound. We also know that the longest wavelength is referring to the fundamental frequency, and this tells us that n is equal to 1. So for a tube open at both ends, we use this formula, and n is of course equal to 1. So the length of that tube is 1.5. We're looking for the fundamental frequency, n equals 1. This is going to help us find the wavelength. Lambda equals 3 meters. We can now go in and find v equals f lambda, substitute in our values, and find that the frequency coming out of this tube is 115 hertz. And that is basically how we do this. Tons more problems and examples coming in class. Tubes that are closed at one end, open at one end, and so on and so forth. Lots of examples, lots more demonstrations.